We're going to prove Euler's theorem in number theory. It says that if we have two positive integers, a and n, of which the greatest common divisor is 1, then a to the power phi of n is equal to 1 up to integers of n, where phi of n is Euler's totient function phi evaluated at the integer n. We're going to see two proofs. One is using finite group theory. The group we use is the group of integers up to multiples of n for the multiplication. So this contains all elements coprime to n. Therefore, a is an element of this group, and we can consider a subgroup which consists of all the powers of a. It's a finite number of different ones because we only have a finite number of elements in the group G. Now we use Lagrange's theorem that says that the number of elements in the group H divides the number of elements in the group G. Therefore, K, which is the number of elements in H, divides phi of n, which by definition of the Euler's totient function is the number of elements in this multiplicative group. Therefore, since this sequence ends when a to the k is 1, we have that a to the phi n modulo n is a to the k times some integer, which is equal to 1 to the power m, because a to the k is 1, which therefore equals 1, which is what we wanted to prove. The second way in which to prove the theorem is to enumerate all the elements in this group G. So let's call them x1, x2, all the way up to x phi n. These are the elements of the group, all the elements of the group G. And then we consider the set AG. Remember that A is an element of G, and therefore AG is again this set, perhaps written in a different order. AX1, x2, AX phi n, and this set is equal to G. The properties of finite groups. And therefore the product I is 1 to phi n of xi, which is the product over G, is the product over AG, which is a to the phi n times the product over G. And therefore, canceling left and right in this finite group, we find that a to the phi n is 1. Again, all in this finite group. That is to say, up to multiples of n. So the last remark is that this is not entirely optimal, although a to the phi n is 1 is the most often cited result, there is a better result by Carmichael, which says that a to the lambda n is 1 mod n. For lambda n, lambda of n is Carmichael's function evaluated at n. And Carmichael's function can be smaller than Euler's totient function. But it won't be treated here.